All right, and let's rock. We are going to continue to talk about cryptography. And if you remember that last time we talked about crypto system, and then we talked about two different types of cryptography. One is called symmetric cryptography, meaning that the decryption keys and the encryption keys, they're the same. And the other is called asymmetric cryptography. In today's lecture, we're going to focus on symmetric cryptography. So first of all, let's just do a quick recall for what is a symmetric crypto. A symmetric crypto is, as I just said, is, Alice and Bob, they're gonna sharing message, but one is gonna decrypt, the other is gonna encrypt the message. For example, Alice is gonna encrypt message and then send the message to Bob. And then they're gonna encrypt and decrypt with the same key. So in this case, KE and KD, which is the encryption key and the decryption key, they're the same. And a good crypto should guarantees that when Alice send, just give me a second, let me turn on my annotation. When Alice send a cipher text C to Bob, and when Bob decrypt this cipher text, Bob should either successfully decrypt it to get this original plain text M, or detect that there's an error. And we're supposing that there is a bad guy, we call it Eve, sitting in the middle, and he or she can eavesdrop, he can spoof the message, or he can manipulate the message. But if Eve gonna spoof the message, then we hope that even if Eve get the cipher text C, she will not be able to decrypt the message. And if Eve is gonna change the message, then Bob will be able to detect the change. Like Bob will not really, after if C's got changed and when get another C prime, which is different from C. So when C prime is not equal to C, then after decryption, say C prime with the key, and this will output error. All right, and just give me a second. Let me take a look at chat. I saw someone of you are discussing. Yes, the reason why we use the name Eve is part of the reason is because it's eavesdropping. And another reason is because like Eve is kind of like evil people. So we use this name Eve. And also like Alex Bob, we're assuming that they're normal people. They're benign people. They don't have any bad intention. And Alice Bob, yes, it's just like representing A and B. Okay, so so far so good. And I will continue. And if you have any questions, just send me on chat or just speak and I will answer. All right. Okay, so let's continue. So back to, we just talked about what is symmetric cryptography, looking at this from a high level. And for symmetric crypto, we can also divide it into two different types of ciphers. One is called stream ciphers, and the other is called block ciphers. And in our agenda, it's not going to be today's content, but like across some lectures, but we will cover stream ciphers, which is something that we're going to talk about today. And we'll also cover part of the block ciphers. And usually when we talk about block ciphers, we want to discuss two questions. One is that, so if we only have one single block, like one single block of cipher text or one simple block of plain text, then how are we going to encrypt or decrypt them? And the next, then we're going to talk about a more practical scenario, which is a message. It's composed by multiple blocks, then how we're going to use block ciphers to encrypt or decrypt those blocks. So remember that for stream cipher, we're going to just talk about that. But then for block ciphers, we need to talk about two content. One is for each block, how we're going to deal with it. And then the second is for multiple blocks, how you're going to handle it. So first, let's talk about the difference between stream ciphers and block ciphers. I know that here I just throw out a bunch of, like terms, right? Like stream ciphers, block ciphers. You may be able to understand it in a very informal and even very coarse way. But now let me just give you a more concrete way to understand the difference between stream cipher and block cipher. So you can consider stream cipher as telephone. You call someone, or say the video that we have right now. So we are communicating. We are doing runtime communicating. Whenever I speak, whenever I utter a word, you will receive the word right away. And similarly for stream cipher, it is the kind of crypto that it will encrypt the entire, like the message as a stream. So it's like one bit of the stream coming up, one bit of the stream got encrypted, and then so on and so forth. And also on the opposite side, if there's one bit of the text got encrypted, then sending it to the other side, that bit will be decrypted. So it's like, it's really a stream. It's doing, the entire cipher is doing encryption or decryption bit by bit. Comparing to that, block cipher is like the text that we're texting each other, right? So it's like we text a message, but then the recipient will not be able to see it until we finish this message and hit the send button, right? So you can consider each time we send a block, although in block cipher, each block is going to be the same size. So if you're going to have a very long sentence, you're going to have a huge text, then the text will be cut into small blocks with the same size, and the size of the block is designed, and it is like it's prefixed according to the cipher itself. So it's like the cipher, the size of the block, and every time when a text or a big chunk or a small chunk, when that text is being encrypted, it's gonna cut it into block, or if it's shorter than the block, it's going to add paddings to be as long as a block, and then it will be encrypted. And similarly, if there's a text, it's a cipher text, going to decrypt it. We're going to use this block ciphers to decrypt the block one by one, and then we're going to concatenate them together. All right, and then next, let's continue to talk about stream cipher. So for stream cipher, the way that it works, as I mentioned, it's gonna encrypt or decrypt the text bit by bit. So the way that it works is that, suppose that there is a key. So this is the key. And in this case, this is an encryption key, because we're gonna use this key to get the cipher text. So this is cipher text. This is plain text. And this is the encryption key. Okay. And the way that works is that the stream cipher will first convert the encryption key to a long key. So it expands it to a very long key, and it is as long as the plain text. And usually this key is called a key string. And also it can also called as pseudo-random cipher digit string. So it is a string. It can be as long as you want, depending on the size, the length of the message. And it uses a function. It's called pseudo-random generator expansion. We're not going to talk about how, like, what is a pseudo-random generator expansion looks like. But I want you to know that using this function, you will be able to get a key string. And then the encrypted message, or say the encryption function, is doing a combination between the key string and the plain text. So if you look at the formula, let's make it a little bit more formal, a little bit math. So this is the cipher text, right? So the cipher text is equal to the encryption function taking K and M as arguments. And what it does is that it will combine the plain text with a converted key string from the original encryption key. And usually this combination is a exclusive OR, so it's an XOR. It can be something else, but usually it's an XOR. So this is the way that a stream cipher makes sure that every bit of a plain text will be encrypted. And again, let me just repeat this. The way that it makes it happen is to expand the key to a key string, a long enough key, so that it will be able to combine with a plain text bit by bit. Okay. And then similarly, for decryption, so you still have the key. And again, do remember that this is a symmetric crypto. So the key will be the same, right? So here you can consider this as an encryption key. Give me a second. I happen to exit my Zoom. Okay, now I'm back. Just one more second. Okay. And this is the decryption key. Although in this case, KE is equal to KD, right? Because this is a symmetric crypto. Oh, crypto. All right. So that is the reason why you have DKC, and then this function is public. It's public for everyone. So whenever who has this key will be able to get GK by themselves, like calculating on their end. And then they will combine this result with the cipher text, and then you will get the decrypted message, which is so far so good. No more questions? Good. And so far so good, everyone. I saw some questions, like Hunter was asking, like, what if the message is very long? Will it be segmented? And the answer is no. They just like, Stu, like, even though the message is very long, every time when a bit of message shows, it will be encrypted right away, because this like key stream will be generated all the time, will be generated continuously, and then it will be used to encrypt those very long message, the plain text also continuously. Okay, so let's continue. Oh, more questions? Can you explain G of K again? Sure. So K is the encrypted key, but usually like the encryption key is something that has been pre-made before, right? So it is a fixed one and it has a fixed length. But we want to generate a key string, meaning that it is long and it's kind of pseudo-random, meaning that you will not be able to predict it, which I will talk about that in later, like just later in this video, you will be able to see that. So G of K, if you're talking about G, the function itself, we call it a pseudo-random generator expansion, because it generates, like expand the key to a key stream in a randomized way. Okay, so I'm going to continue. And I was looking at this chat. I saw some of you guys are asking about slides. So we're not going to disclose the slides before the live session, because usually the live session, we're going to have like live questions, live discussions with you guys. So I don't want you to see the answer right away. But after this live session, I will upload the slides, and also you can watch the videos that I posted online or join the replayed session, the recorded session, and you will be able to get your slides by the time before you go to the recorded session as well. Okay, another question is, how does the person receiving the message get GK? Yes, that is a good question. As I said, G, this function is public. So that means that the function is public, but you will only be able to get GK only when you know K, right? So this comes to the question of how a symmetric crypto should share their key securely, which we will talk about not today, but sometime in the future. So how to do exclusive word on the string? That is a good question. The way that works is you first convert string to bit string. So for example, if you have letter A, then you got an ASCII, right? So I remember letter A is 61 in ASCII. Correct me if I remember that wrong. Or guys, please just do me a favor and search and see if it's 61. Is it 61?
I think it's 65.
Oh, thank you. Right, okay. So A is 65, and okay, that is capital A. Good, thank you. So capital A is 65. Then we want to convert 65 to bit. So you can do that by, well, I'm gonna just do in the math way that I know of. So it's gonna be 65, I just divided by 2, so it's 32. Got the remainder 1, and then, okay, oh, actually, there's another way. It's much easier. So 64 is 2 to the 6, right? So it is 1, 2, 3, 4, 5, 2 to the 6, and then plus 1. So this is 65. So in this way, you got this bit for A. And guys, I saw two answers. One say capital A is 65, the other is small case A. Let me just search online because I want to give you the most accurate answer. Calling Python is the fastest way. I'm just do Python on my end and do a word of A. All right, so the capital A is 65 and the lowercase a is 97. All right, so now let's look at just the capital A. So this is the way that we can convert a a letter, like which is a character in the string, to a bit string. Someone is saying that the binary is missing a 0. Let me check. Actually, since I'm already using Python, I'm just gonna do that on Python. It is 1, 2, 3, 4, 1, 2, 3, 4, 5. You are right. So it is 5 zeros in the middle. So you have 5 zeros in the middle and then 1 in the end. So this is the correct answer for capital A. Although in real world, what we're going to do is we're probably going to add some more 0 before this, some more 0 before we convert that, because we want to make sure that every character, it has the same size. And usually for a character, you can consider this as, for ASCII, it is 256 bit. So you want to make sure that you have like 8 digits for each of the character. All right. Any more questions? Good. Okay, I'm gonna continue. And so far so good, everyone. I'm just giving you an example of how to convert a character to binary. All right, I'm gonna continue. Let me clear this out. Okay, so the question is stream cipher secure? The answer is yes. If the pseudo-generator GK is unpredictable. Also, if the key string is as long as the plain text. And for the second one, which is easier to see, is that if the key string is not as long as the plain text, then some of the plain text will not be able to combine with a key string, right? So there will be like some plain text will be just rawly, like say barely just like show right over there. So you will see that that is exactly what a plain text, that is even after the encryption, you know that it's the plain text and you don't want that to happen. So you want to make sure that the key string, when it is combined with plain text, is as long as the plain text. Okay, and the other is about the first one is a pseudo-random generator is unpredictable. So there is a specific definition for what it means by unpredictable. You may think that, you know, just like randomly generate a random number, that will be good enough. But there is a more precise definition for unpredictability. Sorry, I'm really bad at English. Unpredictability, right? Unpredictability. Thanks, Thomas. So for that, what it really says is that given a generator, or say if you don't know the generator, say that you don't know how exactly G is calculated, but you know the historical data, you know that GK's value in previous days, like 1 second before, 2 seconds before, like many times ago. So you know like a sequence of generated output, but then you will not be able to predict future output based on those historical data. So that is what it is precisely mean by unpredictability. And you don't want that to happen. So that is about, you don't want your pseudo-random generator is something that the attacker can predict, because if attacker can predict that, then attacker can collect the previous behavior and then predict the next state of the generator so that it will know the exact value of GK. And the second is that you want to make sure the stream is long enough so that every bit of the plain text will be combined with a key string. So one of you guys asking, can I give an example of a key string would look like? A key string is a bit string, just like 0101, a lot of zeros, a lot of ones. That is a normal key string. And this is generated by pseudo-random generator. And when I say this is generated by pseudo-random generator, it means that this generator itself is just like generate a pseudo-random number according to the key that we give it. And then one will convert this number, like this generated number coming from GK to bit. And the way that it converts from like a number to a bit stream, it's pretty straightforward. It's just like convert it from 10 base integer to a binary. Right, this is just a random binary string. Cool. So this is about stream cipher, and actually I want to make it more general, and then I want to bring in this term. We call it the one-time pad. So one-time pad is another type of cipher, or say it is, I would say this is very similar to stream cipher. You can consider this like a Caesar cipher. It is just yet another type of cipher. It's another type of crypto system. So it is invented by Miller and Vertnam in 1882 and 1917. So the way that it works is very simple. It's very similar to stream cipher. I would say actually modern stream cipher is inspired by OTP, the one-time pad. So the way that it works is that the encryption is always the ciphertext, which is the encryption function that's output, right? So that one is always equal to the XOR of the key and the message. And also, on the other hand, the decrypted message, the ciphertext, is always equal to the key XOR C. And this makes sense because if you just do this, suppose that you have an M. You have M, and then you want to convert that to C, okay? So the way that it works is that it's gonna use K XOR M. This is the C. And then suppose that this is Alice. We're doing this Alice Bob scenario again. So, and then this is gonna send to Bob, right? And suppose that Bob will get the same message. So Bob didn't get a manipulated message, which actually I will talk about that later. What if Bob got a manipulated message? Let's just keep it in mind, and then we'll get back to this later. So Bob get this ciphertext, which is the same as what Alice managed to encrypt, and then Bob wants to decrypt it, okay? So when Bob is gonna decrypt it, it's gonna do the M from the Bob's perspective is gonna be C. Let me just do this exactly the same as what I write over here. I'm not gonna switch it. So it's K XOR C, right? Which is K XOR K XOR M, right? And we know that in this case, it is equal to M, because if we just XOR a number for twice, it's equal to not XOR it at all. Okay, so now we get Bob's message equal to Alice's original plain text. So we know that mathematically, this encryption and decryption, they're correct. Like you can get exactly decrypted message from an encrypted message. All right. And then let me just continue. The question is, can you infer K given an M and a C? Yeah, I saw many of you guys say yes, that's correct. Exactly, K is equal to C XOR M. And that's a problem for a one-time pad, which is that if you know M and if you know C, it's very easy for you to infer the key, right? So then the question is how to avoid this? If you keep changing K, can you infer M given C? Exactly. I saw Dean saying that, but no, it doesn't mean anything because it never is reused. And that's correct. And this is exactly why this is called the one-time pad. So the key, K, will only be used for one time. So you just keep changing K, and then even though you got the C, you got the cipher text, you will not be able to infer the plain text because the K, as I said, the one-time pad, the key is going to be changing all the time. Great. And in fact, I mean, this looks pretty simple, right? It's just an XOR. And then very interestingly, that this has been proved that it has a what is called a perfect secrecy. So perfect secrecy, there is a formal definition, but we're not going to touch it. Just I'm going to speak this informally. Perfect secrecy is we're not better off determining the plain text when given the ciphertext. So that means that even though we know about the ciphertext, we will not be able to guess out the plain text with higher probability. By the way, guys, I noticed that there's some problems with my current annotation. I cannot remove those blue lines. So I will try that later, but right now let's actually, just give me a second. Let me see if I can do something to remove that. I'm using Zoom's annotation and sometimes it's not very stable. It still doesn't work. It just be there. Very interesting. Okay, here we go. So back to this perfect secrecy. So it says that Shannon has proved that OTP, one-time pad, has perfect secrecy. So it means that an attacker, even though the attacker is spoofing the communication channel, even though that he gets a ciphertext, there's no way for the attacker to guess the plain text with a higher probability, even though she knows about the ciphertext. So OTP is great. If you look at some movies from talking about World War II, or you look at some TV, some dramas about those, sometimes you will see that someone just have a code book, right? Like some book, maybe it's a fiction or something else. They just open it to turn on some page and they try to get something out. And then they use that as the key to decrypt their message. And maybe someday later they use another page, they got another stream as their key, and then they do another decryption. So that is the way that we change the key. That is the way that they enforce an OTP. They just reuse a existing literature like a fiction or something else, and they have a rule that has been predefined before about which day you're going to look at which page, and then you use that as a one-time path, OTP, as the key to decrypt or encrypt messages. Okay, so now I want to ask you a question. What if we just relax this a little bit? What if we make it as a two-time pad? So every time we're going to use the key for twice, we're going to have the key to encrypt two messages. And then we're going to send this message to the recipient. Is this secure? And I want you to spend some time to think about it. Okay. So I saw some of you are leaving a annotation, or also some of you are trying to leaving leaving a message in chat. So I'm giving you a hint. What if eavesdropper gets both C1 and C2? Okay, and it's Dean says that the second message is not secure because you can infer the key from the first one, right? And then Ryan says that, yes, if attacker has C and M, they could infer K, it's the same, right? And then decrypt the next message. So it's secure half the time because it can always just decrypt the second message. And Jordan is giving a better answer. So it's not only that you can decrypt the second message, and in fact, you can also decrypt the first message. Right, so you could compare ciphertext and infer the key. And if you get the key, then you can just get all the message. Okay, so now I'm going to talk about this answer. I mean, the answer is all you guys are correct. This is not secure, and there's many ways to attack it. And one way that you can attack it is that, let's suppose that eavesdropper gets C1 and C2. So if eavesdropper gets C1 and C2, then he can or she can do an XOR on this two message. And then you can get this XOR of the plain text, because in this way, even though you do not know K, by doing C1 XOR C2, K just got canceled out because you do XOR K for 2 times, right? So you got the XOR of 2 plain text. And it turns out that if this is English, then, or say some Latin language, and then having a 2 reasonable message and then XOR it, get this XOR is good enough for us to infer the message of M1 and the message of M2. And in fact, very interestingly, this happens in the real world. So there's a project called Project Banana. It is from 1942 to 1945. And Russians use this OTP for twice. So it's similar to this like 2-time path. So just use the same OTP for twice. And then this crypto system was broken by American and British cryptographers. So you see that there are people that real world that they use this OTP as a 2-time pad, and then it is broken by the other group of people. So you don't want this happen in your world, and then you don't want this happen if you're going to set up a crypto scheme. So that is a very interesting example of how 2-time path could fail in securely decrypt and encrypt messages. Okay, so back to this question, is Scream Cipher secure, right? And then I said about this unpredictable property. So I'm going to give you a more formal explanation for unpredictability, okay? So predictable means that if there is a PRG, this is like pseudo-random generator, PRG. If pseudo-random generator G is predictable, then, or say, actually, let me just re-say that because this logic order is wrong. So PRG, let me just write this down, pseudo-random generator, right? Pseudo-random generator. I'm not sure if I spell pseudo correct. It looks like something wrong, but just pardon me if there's a typo about that. So for pseudo-random generator, G, it is predictable if there is an efficient algorithm. We call this algorithm as adversary, okay? ADV representing for adversary. And let me correct my spelling. Pseudo-random. Thank you, Dean. Cool. So if there is an algorithm, ADV, such that this algorithm will be able to get a probability of, a future generated value from the pseudo-random generator greater than 1/2. Because here, when we say this means that at a particular time that this pseudo generator is going to generate a bit. So this is the I+1 bit. Okay, so it has only two possible values because it's a bit. It's gonna be either 0 or 1. And this is saying that if you know the previous bit from, say the first bit into the ith bit, and you want to predict the I+1th bit, and this algorithm, if there exists an efficient algorithm, usually when we say efficient, it means maybe this is polynomial, like not something that's exponential, or even though it's exponential, it depends on exponential, exponential to what? But like in general, this is efficient enough such that we can have a better prediction for whether or not the next bit of the pseudorandom generator generates is 0 or 1. And then also here, this is non-negligible. And usually we set this to, this is a huge number. I mean, this is a small number because 2 to the 30, but still, when this is large enough, it means that it has a shift. It's not going to be neutral. It's not going to be someone just guessed as half and half, like for 0 or for 1, but someone really has a preference for which bit, like or 0 or 1 has a better chance to be the next bit. And this is going to be called predictable. So this is called that PRG is predictable, and we don't want this happen. So we want to make sure that there is no such algorithm that will have a correct and will have a correct and uneven preference for the next bit of the pseudorandom generator, given the previous bits from 1 to I, some previous historical bits generated by this pseudorandom generator. Okay, so far so good. All right, I'm going to continue. Cool. And then now let's talk about integrity, about stream cipher, as well as the one-time pad. Now we come back to this question, right? So because remember, originally when I talk about, where is it? Here, right? When I am talking about one-time pad, and then when I was showing you this, so we're saying that let us assume that the message that Bob received, which is the encrypted message, doesn't change through the channel, through this like public communication channel. But then the question is, what if really someone is changing it? What if there is an Eve in the middle and then Eve tries to change this value? And here is the Eve, arrow people, right? This is Eve. So what if Eve is changing this encrypted value to someone else? So this is this C prime, which is different from C. Okay. So if C prime is there, if someone just changed C, is there a way for Bob to realize this change? Can Bob detect the change caused by Eve? And unfortunately, the answer is no, because according to the way that Bob is going to decrypt, which is to X or K, there's no way for Bob to tell that the stream got changed. And in this way, we cannot guarantee integrity for stream ciphers. So this is the bad news for stream cipher. Usually stream cipher, they just either made this problem, use other way to guarantee integrity, or they just like add more designs, like more layers of the design in order to guarantee integrity. And we're not going to talk about that in our lecture, but if you're interested, then you can just check those real world stream cipher example. For example, RC4 is one of the most favorite and the most popular stream cipher in real world. It was used for many years. I think it's about 10 to 20 years. So RC4 is invented by Ron Rivest. And if you don't know Ron Rivest, you probably want to know him because he is quite famous. He is the R in RSA. So we were talking about RSA, which is another encryption scheme. But for now, I want to know that Ron Rivest, he is a very successful and very well-established professor, expert in crypto. He's very great, and he invented RC4. And although there's weakness in RC4 that is identified later, actually some of the attacks is identified by Ron himself. RC4 had been used for decades in many protocols. For example, RC4 was used in TLS. And TLS is, a well-known security protocol still being used right now. But because of the weakness of RC4, TLS stops using RC4 in 2015, which is quite close to us. And another protocol is WEP, it's a wireless protocol. So for this protocol, it uses RC4. And in fact, because of the weakness, because of those attacks figured out by security researchers later on, RC4, it harms WEP. And that is part of the reason you don't want to use WEP anymore for your Wi-Fi, because it is known to be not that secure. And you don't want that to harm your Wi-Fi security. Okay.
A question about streaming ciphers. Is it still kind of okay for stuff like video and audio? Because would it be hard for somebody to mess with the integrity of it and us not notice? Like if I'm used to talking to my mom, for example, if somebody were to try and interrupt that and my mom didn't sound like my mom or it was corrupted or something, wouldn't that be easy for me to detect and be like, oh, something's bad's going on? So is it still good for stuff like video and voice?
That's a good question. I think so. And I believe there are still many stream ciphers that are used for stream, like the videos that you just mentioned, because even though someone is gonna sit in the middle and then change the bit, it's not gonna influence too much. It's not gonna impact your overall experience with your mom or with other people who's gonna chat with you. And I agree with you. Like stream cipher, I'm not saying that stream cipher should be abandoned or should be just prohibited for good. And in fact, there's still many stream cipher being used right now. And since you just mentioned, let me see if I can turn on the slides. Give me a second, because when I say the weakness of stream cipher, I also want to emphasize the advantage. Yes, stream cipher has this security weakness, but it doesn't mean that we should just not use it anymore. And in fact, stream cipher has a very good advantage, which is it's super fast. It's super efficient. This is due to the design of stream cipher. As you see, the way that it combines key stream and the plain text is very fast. And XOR is a very fast calculation. So that is the reason why, part of the reason why stream cipher is still prevalently used in real life. And guys, just give me a second. Something wrong with my mouse. I cannot go to the next slides. Just a second. Okay. So here, this is something that I want to show you guys. So stream cipher and block cipher, there was a performance evaluation. There was a comparison in terms of performance between these two types of ciphers. And as you see here, for a stream cipher, the throughput is relatively larger than the block ciphers. So usually for stream cipher, you can get hundreds of MB per second, which is pretty fast. And then for block cipher, 3DS, we will talk about those block ciphers later on. But for 3DS and AES 128, which is quite popular, that is AES is still used. DS is no longer be used very popularly, but like AES is a very popular block ciphers using right now. And you see that the throughput is not as good as stream ciphers. So there's definitely advantage of stream cipher and people are still using it. Okay, and then now coming to the block cipher part. So as we talked about this before, so for block cipher, usually we just cut a plain text into blocks, a block with the same size, and then we encrypt the block to ciphertext or decrypt the ciphertext block to plain text. And we're using the same key for encryption and decryption because this is also symmetric cryptography. Usually those ends at the K, which is the size of the plain text and the size of the key, is predefined according to the crypto system. So for example, for 3DES, which we will mention not in today's lecture. We're going to talk about DES for today's lecture, but not for 3DES. So usually for 3DES, it's the size of the plain text is 64 bits, and then the size of the key is 168 bit. And then for AES, usually the size of the plain text or the size of the ciphertext is 128 bits. And then the key can be either 128, 192, or 256 bits, depending on how secure you want. And usually the longer the key is, the more secure it is. Okay, and then this is performance, we just talked about. And then let's go to the block cipher part. So today we're going to talk about only one question, and we will not even finish this. But I would like to start to talk about block cipher. Sorry, this is not blocker cipher. This is block cipher. Let me remove this block cipher. And we're going to look at how to encrypt or decrypt a single block. And in next lecture, or maybe the next lecture, depending on how fast we are, we will talk about how to operate on multiple blocks. Okay. And I will start with DES, one of the very famous block cipher. So I want to know, how many of you have heard about DES, this cipher, before? If you know it, you can just say yes in the chat. I just want to have a course feeling about you guys' experience. Good. Okay, I saw many of you say no, some of you say yes, a bit. Okay, good. That's nice. And I'm pretty sure that after today's lecture, you will know DES very well. And then I hope that you will not only just know DES, but also appreciate this very delicate design. Like when I look at this, I'm just feeling, this is like, wow, amazing. I don't know how Horace Feistel managed to come up with this very simple but beautiful network that can support a encryption and decryption system. But I was just like, oh, this is how beautiful. This is so elegant. So history about that, DES. First of all, in early 1970s, Horst Feistel designs Lucifer at IBM. Lucifer is another crypto system. And in this, I would say Lucifer is like ancestor of DES. DES is something that has been modified based on Lucifer. So Lucifer has a key of 128 bits, and the block size is also 128 bits. And then NBS asks for block cipher proposals. That is the time that NBS is looking for a standard block cipher that like is public, then people can use it as a standard. And then IBM submits a variant of Lucifer. And later on, Lucifer was selected, and then they changed this a little bit, and then they changed the name. Also, they call it DES, and then use it as a federal standard. And if I remember correctly, DES represents for data encryption standard. I forgot the exact name of DES, but if you guys can Google it right now, please just Google it and then post it your answer in chat, and I will tell everyone what DES represents for. Okay, so this is nice. DES becomes a federal standard. Yes, data encryption standard. Thank you, Ryan. Cool. But then later on, you see that like 20 years later, almost 20 years, 19 years to be precise, DES got broken by exhaustive search. And this comes to the attention to the organization, and then they would like to have a new standard block cipher. And this comes into play AES, another cipher system that I will talk about, a crypto system that I will talk about in future lectures, not today's. But then later on, AES replaced DES. And then now AES has been still very popularly and widely deployed in many systems, like banking, commercial systems. And then DES has got a little bit outdated, I would say. Okay, so now let's go to, Now let's go to the actual math of DES. And here I want to make this part slow, especially when I talk about math. So if you have any questions about those math, please ask me right away so that I know that you're on the same page as me. Because if you miss any tiny bit from the slides, you may miss the entire letter part. So please make sure that you can follow me. Okay, so the core idea. I'm going to start with Feistel network. Okay, so let's suppose that there is a one-way function. What does it mean by one-way function? It means that this is a function that you can very hard to reverse it. Like you know how to convert. You can how to convert some bit string. Let's say this is, for example, I'm just writing a random byte, okay, to another random byte. But it's very hard if you know this function, right? Maybe this is F1, I'm just call it F1. And then it's gonna be very hard for you, almost impossible for you to know what F1 reverses. You cannot really reverse it back. So consider this as a, for example, like a hash function. So suppose that we know about those one-way functions, okay? So you're given that, and your goal is to build an invertible function so that you can use this invertible function to encrypt and decrypt using this one-way function, okay? And now let's consider the following. This is a plain text, and we're going to divide plain text into two parts, left and right, okay? And each of them, they have the same numbers of bits. Okay. And now we're going to convert those RL, the different half of a plain text, to the next layer. We call it R1 and L1. So far, let's only look at this particular one because the rest is just iterative. Okay. Let's only look at this part. So let's see, what is L1 equal to? So L1, like R0, part of it just directly go to L1, right? So we have L1 is equal to R0, okay? And then R0 goes into this one-way function, and then it XOR with L0, okay? So, and then after this, the output goes to R1. So R1 is equal to L0 XOR to F1 of R0. All right. So far, so good. Can you catch the, the conversion between the figure and the equations? Okay, I didn't see anyone saying no, so I'm going to continue. And then let's make this more general. Instead of saying L1, R1, and L0, R0, we're going to just use I and I plus 1 to represent that. So this goes to this. All right. So here you see this is the same as this part, right? We just do Li instead of L1, and Ri minus 1 instead of R0. And then this equation go to the other equation, where we have I is 1, and I minus 1 is 0. It's the same. I just generalize it using I instead of using 1 and 0. Cool. Okay, now I'm clear this up. You don't have to remember those. All you need to remember is this. Okay, this equation. Now let's continue. So the question for you is that, suppose that we already have this network. And then suppose that we know, given this one-way function, and we define Ri and Li as the follows, as this. Ri is equal to the Fi of R I minus 1 XOR L I minus 1. This is the same as what we show here, right? Like this equation is the same as this. I just copy paste this again, okay? So now, how can you construct an inverse function for R minus 1 and L I minus 1 so that it will be able to deduce from the equation like this? I'm going to give you some time to think about this. So in other words, we're asking you how to, like, what is the inverse function for Ri minus 1 and Li minus 1 given that those equations? Can you calculate it? Right? Peter's first part is right. Ri minus 1 is equal to Li. And what about Li minus 1? Okay, Dean's answer is closer. Is Li minus 1 is equal to F L. I am copying Dean's solution. Just give me a sec. I minus 1, right? Okay. Yes. Good. Let me check if Li minus 1 is correct. Yes. So it's going to be that. Cool. Okay, so this is Dean's answer. Anyone else agree or disagree with Dean? Okay.
Shouldn't the input to that function still be R of I minus 1? Because I don't think you can put in the L of I and expect to get the reverse back.
So the input of the function is going to be Ri and Li. So you want to get the, like, representing Ri minus 1 and L minus 1 using Ri and L. You can consider this as an encryption. And now you're trying to do a decryption. Make sense? Okay, so I saw some of you are still confused. Let me explain this. So the question here is that if you are knowing, if you're given one-way function, okay, and then you know that this is the value of how Ri and Li is calculated given Ri minus 1 and Ri minus 1 and Li minus 1. Let me just write here. Given that, and then given this, and then the goal for us is to calculate Ri and Li. Okay, so this is the first part. And now I am asking is, if you are given a one-way function, and then given Ri and then Li, and how to, or say question is how to calculate I minus 1 and L I minus 1. Is it clear?
Yeah, thank you.
Cool. Okay, and this answer is correct. So let me.
My question was that how is that answer correct? I understood the question.
Mhm.
I just couldn't understand how we got to the answer.
I see. I will show you. That is a good question. I will show you how that is got. So this is the answer, and Dean's answer is correct. And then now I'm going to talk. I'm going to show you how we get this. Okay. And it's not hard to get this. I'm pretty sure that you will understand this. So now we know that Ri is equal to this, and Ri is equal to this, right? So the first thing, let's try to get Ri minus 1. Because in this equation, we already know Li is equal to Ri minus 1. So if we know Li, then Ri minus 1 is equal to Li, right? According to this equation. Did you get that?
Yep.
Cool. Okay, so now we know that Ri minus 1 is equal to Li. And then let's look at this equation. Okay, so we have that Ri is equal to Fi of Ri minus 1, and then XOR Li minus 1. And then the goal for us here is that we know about Ri, we're assuming that that is given. And then for Ri minus 1, it's unknown, but we just get from this equation that Ri minus 1 is equal to Li. So we just change this to Li now, which is also given, right? And then we want to calculate Li minus 1, and that is equal to, you just do plus Fi from both sides again. So you will have Ri XOR Fi Li equal to Fi Li XOR I minus 1 XOR Fi Li. All right. And then this got canceled out because XOR. So that is equal to Li minus 1. That's how you can get that Li minus 1 is equal to Ri XOR Fi of Li. Okay, good. Okay, I saw Benjamin says yes, so I will continue, but if you don't understand, just let me know. So now we got this equation, right? We got that if we are given this, Li and Ri, and then of course those f function, we will be able to calculate R I minus 1 and L I minus 1. And then let me do one more. One more thing, if we just like draw this in the network in the way that we draw the previous calculation. So we see that this actually looks pretty similar, right? Because all we do is we have, we divide a message into half and half, and then we use one half to directly get the next half, and then the other half we do a one-way function and XOR the other half. So this is exactly the way that Feistel uses this network to do encryption and decryption. And the way that it works is that, say this is encryption, and this is decryption. So given a plain text, and then given all those functions, one-way functions, they can just use this plain text and then to divide it, do a time of the conversion that we just mentioned about, and then do this for the second time, again, iteratively, until we got the ciphertext. And usually they have a fixed number of conversion. In that is 16 times. Okay, and similarly, if you're going to do decryption, you convert from a ciphertext to a plain text. You also use this way to, convert the ciphertext by 16 iterations, and you will get the plain text. And then the elegant thing here is that although those F1 and then F2 and FD, they're one-way function, right? So their one-way function means that you will not be able to get the inverse very easily. Like you cannot get the inverse of those one-way functions very easily. However, by building up this, we call it Feistel function, the Feistel network, like each of this, it is a Feistel function. Usually it is used big F to represent that. You give it this inversible property, right? So you can inverse it. You can decrypt and encrypt using this F function. But then for attacker's perspective, if attacker doesn't know about this F1 and F2, even though the attacker knows about the F function, knows about like the equations here, there's no way for attacker to recover the cipher or the plain text given the ciphertext. So this is why I feel that, okay, this Feistel network is so beautiful because it enables this inversible property using inversible functions. Okay, so I got questions from the asking, so does the key describe which functions are used or not? The answer is not, but we'll come to this very quickly. So how keys come into the play, right? This is exactly what this was want to ask. It looks like so far we haven't talked about key at all, right? So how we're gonna have key here? One second, let me clear this out. Okay, so the way that the key works is that the key itself is gonna be in part of this one-way function. So it is those one-way function, they're fixed, but then those one-way function has both the X, like which is R0 or L0, depending on depending on its decryption and encryption, as well as the key. So this is maybe L0, R0, and then this is the key. So the way that it works is that those one-way function, they're gonna take key and maybe part like this R0 as input, and then it's gonna output something. And in the DS, in the DAS system, the key originally it's 56 bits, and then it will be expanded to have 16 keys. And each of the key has 48 bits. It has a like predefined key expansion algorithm, which I will mention that later. I'm not going to talk about how exactly that works, but I will talk about like the nice properties that key expansion system wants to keep. So it has those keys, and then it's going to combine them together. This is how key comes into play. And then it has an initial permutation and a final permutation. And the reason why this exists is because they want to have these two functions to be coordinated with the original like hardware design in middle 1960s. Like it has no crypto or no security properties. There's no necessary, it's not really necessary to have these two, but originally, because of hardware efficiency issue, they have this IP and FP, the initial permutation and the final permutation, both like these two permutations, they're always just inverse. But now we don't have it, but because the DAS standard has been made, we just like keep it as what it is. Okay. So we are running out of time. I am going to just leave it for now. And then in the next lecture, we're going to talk about the details of the DS design. All right, everyone, this is pretty much for today. And I'm sorry that we not only running out of time and make it late for 5 more minutes, but that's pretty much for today. And if you have questions, feel free to, ping me in Slack, sorry, not in Slack, in the Piazza, or send me an email, and I'm happy to help you. See you next week.